All right, today we are pulling back the curtain on a piece of engineering that, let's be honest, millions of us trust with our lives every single day, but we almost never see it. We're going to dive deep into the hidden world inside elevator shafts, and we're guided by a fantastic technical breakdown from the specialists at Novin Pooya Elevator.
I mean, really think about it. You press a button, the doors slide shut, and you're just lifted or lowered dozens, maybe even hundreds of feet. And it's also smooth and quiet. But what's the fundamental thing that makes this modern miracle even possible? And more importantly, keeps it incredibly safe?
Well, it's the steel framework inside the shaft. It's this meticulously engineered skeleton. This thing is the real unsung hero that bears all the weight, guides the movement, and has to be ready for the totally unexpected. So let's take a look at what this backbone is truly up against.
You know, this structure is in a constant battle with physics. I mean, a serious fight against an incredible array of forces, 24 hours a day, 7 days a week, for decades on end.
First, you've got what are called static loads. This is just the relentless, never-ending dead weight of the system. Just imagine the sheer weight of the steel guide rails. Those are the tracks the elevator car runs on, stretching the entire height of the building. Add to that the heavy doors on every single floor, all the machinery. It all just hangs on this structure all the time.
Then, things start moving, and that's where dynamic loads come in. This is where it gets really interesting. Every time that elevator car starts to move, that acceleration generates a powerful force. Every time it slows to a stop, that deceleration creates another force. These are the active, powerful stresses of pure motion that the structure has to absorb just seamlessly.
But the engineering has to account for some really extreme scenarios too. I mean, if you're in an earthquake zone, it has to handle seismic loads. For those beautiful glass elevators you see on the outside of buildings, it has to brace against powerful wind. And then there's the big one, the most critical one, the safety gear load. Okay, so here's the bottom line. If the absolute worst happens and the emergency breaks, basically the elevator's parachute have to engage. The structure has to absorb that violent, instantaneous stop without bending, without breaking, without deforming at all. The integrity of this backbone is literally what stands between a safe stop and a total catastrophe. So how on earth do engineers build something this incredibly strong? Well, they generally start with one of two main design philosophies. First, you've got the traditional approach, which you could call the concrete fortress. This is where the elevator shaft is actually formed with reinforced concrete walls, right as part of the building's main structure. It's unbelievably strong, but the real magic is what's inside.
The second approach is what you can think of as the steel cage. This is a full, self-supporting steel framework that's built either inside the building or even on its facade. It's like a complete, independent skeleton for the elevator.
So, how do engineers choose between the two? Well, a concrete shaft gives you fantastic fire resistance, and it's great for dampening sound, but it's a lot less forgiving. If you misplace those steel mounting plates during the concrete pour, that can be a very, very expensive fix. The full steel structure, on the other hand, is much faster to install. That makes it perfect for retrofitting elevators into existing buildings or for those panoramic designs where all that beautiful steelwork is actually part of the view.
Now, the choice of structure isn't just about the building itself. It's also deeply, deeply connected to the type of elevator technology you're going to use. The machine itself basically dictates the design of its home.
Yeah, different technologies put very different demands on the structure. A hydraulic elevator, for instance, it pushes the car up from below, so it has pretty low dynamic loads. But a high-speed traction elevator, with its massive counterweights, generates enormous forces that demand a heavily reinforced frame. And then you've got MRL, that's machine room-less elevators. These are so cool because they move the motor from a separate room inside the shaft itself. But that means the entire structural backbone has to be engineered with these hyper-specific vibration-dampening anchor points. This is exactly why the slow, steady ride in a 3-story office building feels so different from that rocket-like ascent in a modern skyscraper. Their hidden structures are fundamentally different.
And this is where the engineering really gets pushed to its absolute limits. In these special cases, from elevators that climb up the outside of buildings to those that service the world's tallest skyscrapers.
A facade elevator is like a triple threat for engineers. First, the structure is constantly being pushed by the wind, so it needs extra bracing. Second, it's exposed to rain, sun, you name it, so every single piece of steel needs advanced protection against corrosion. And third, because everyone can see it, it can't just be strong, it has to be beautiful, a part of the building's architecture.
And then you have super tall skyscrapers. I mean, the buildings themselves sway in the wind, and the elevator's guide system has to just roll with that movement. The dynamic forces at speeds over 10 meters per second are just immense. But maybe the biggest challenge of all? Maintaining perfect alignment across hundreds and hundreds of floors. And this brings us to the single most critical detail of this whole thing.
After all the complex calculations about forces and materials and wind, at the end of the day, success or failure comes down to one thing: precision. Unbelievable, almost microscopic precision.
Take a look at that number. Less than 2 millimeters. That is often the maximum allowable deviation for the alignment of the guide rails over their entire length. We are talking about a tolerance that's less than the thickness of 2 credit cards stretched over the height of a multi-story building. Just wow.
So why on earth are they so obsessed with this level of perfection? Because any tiny deviation, anything more than that, and you're going to feel vibrations, it's going to cause premature wear and tear on all the components. Ultimately, this microscopic precision is what separates a rough, noisy ride from that feeling of just floating. Perfectly smooth and silent, which is what we all expect from a modern elevator. It is the final guarantee of quality and of safety.
So the next time you step into an elevator, just for a second, think about that unseen steel backbone, engineered to battle physics and aligned with microscopic precision. It kind of makes you wonder, doesn't it? What other incredible, hidden engineering is working all around us, keeping us safe every single day?